Okay, guys, so we'll start.
Can I do like five minutes?
Sure, of course.
I have that one.
To get this card? Hopefully.
First, I have to show the report.
Yeah, of course. So let's see now, where are we? So next, we schedule some talks, right? So hold on, so Saturday kab hai? 7th, and then 14th we schedule, right?
Yeah.
So on 14th, who are speaking? 3 talks, we said, right?
Yeah.
So Saurabh, Sunanda and you. And then we had April 13th, right? Who were for April 13th? 2 people. Agnew was there. And who else?
Shantanu will define the sequence integration and
That's right.
lectures.
So then how do we do this?
Yeah, I mean, Shantanu should go before.
Yeah. So then how do we do this?
Agni Shantanu should.
You saying have 3 talks on that day? On April 13th?
So Praveen
I
is
guess
on
we
May
can,
11th.
right? Huh?
Praveen is on May 11th. This is May.
Oh, it's on May. 2022, right?
Yes.
Can't get these things.
Praveen is on May 11th. Yes.
Huh?
Praveen is on May 11th.
For me, it's May, right? That's what you're saying. Okay, so that's good. So then we're all set, right? Now May 11th we have this talk, but that's in the morning. By Vidyasagar. So Vidyasagar is giving 2 talks. These are good talks for us. These are stochastic approximation. Machine learning is a very well regarded person in control theory. So he's giving a colloquium Tuesday 4 to 5 p.m. Reinforcement learning, stochastic approximation, and then he'll delve deeper on Wednesday 10 to 11 to 12 p.m. So we can have one talk, Praveen's talk maybe 4 to 5 p.m. or something Tuesday. Okay, so we'll have May 13th, we'll do 3 talks then. So you're saying we'll have Shantanu first?
He will introduce sequence integration and
Guys, this is, listening to so many talks at one go, and if they're not well prepared, it's very demanding on the audience. Just prepare very well. In the sense, organize your thoughts, be clear about, the bigger message, so to speak, so people can follow. And then you bring out the details, proofs, etc. What is the problem? Why is it important? What are the key results? So those are things you talk about first. Set the stage, and then you say, okay, in the result, this is the key interesting part. This is what the key steps of proofs are. So if you just give, it's going to show a lot of notation which people are not able to follow in the time, and then that's kind of very demanding. So just be. That's why I thought having 3 lectures is both ways is quite big. But I guess we get them faster. Right. I mean, we could move Agnew to Monday if you want. If that's okay. 17th,
13th is which? 13th is which?
Okay, this Saturday.
14th is Saturday. So 14th is Saturday? Doesn't sound right.
Yeah, 14th is Saturday.
I see. Okay. So we could move Agnew to 16th if people are interested. You would like that, of course. Is that okay? Shall we do it one person 16th? Yeah. That's good. So and now we said on Monday. Let's keep it 4 p.m. for now. And then I think Praveen is what date? Praveen is May 11th, we are saying 4 p.m.
Yeah, yes.
Here, Praveen. Yeah. Is that okay, Praveen?
Yes.
Okay. I don't know what you're going to speak on, so just let me know. Huh? We probably, yeah. Okay. So that's the agenda. Let's move on for today. So I thought before we call it a quits, let's just have a couple of lectures on Brownian motion. So that's the plan. It's always kind of you would have seen some of this at least formally in the lecture. Now the reading it probably a bit interesting. Okay. This is going to be lectures from Michael, right? Michael Steele. Yeah. It's a very nice book. I don't know how much you read it already, but yeah. So continuous time process. I just give you just of some interesting things as you go ahead. I won't go into. You don't have time to go through each and every detail. Just some details and some big things. School properties. You start at 0. Second is the increments. Are independent. So BT2 minus BT1 BT4 plus 2 the increments are independent. So that should not be, it's not that surprising. We've seen independent increments before. Do you have an example of that? Poisson process, exactly. There's also the increments are independent. In commonality with Poisson process, we'll say that okay, BT plus S minus BT is distributed as normal 0. S for all S in T. So that's the other property, that increments are stationary, they just depend upon the length of the interval. But very diverse. And they're Gaussian distributed, mean 0, so always remain B0, and variance which is given by the length of the interval. The fourth was, okay, this is interesting, that BT omega is a continuous function of T for all omega in a set of probability. So paths are continuous. So this we discussed right in, I guess, first lecture of the course, right? Was that?
BT.
Oh,
Wait, sorry,
BT.
yeah. It's a random variable, right? So we are hiding omega, but it's always there. It's as a function of fix and omega, you just observe it as a function of t. It's continuous on a set of probability one. That's very important. The big issue, as we said, was okay, can you construct such a process on a probability space? So that I will not talk about in this course. There's a good proof using ideas from wavelets that in any case is fun to read. That's given in this book. First proof was by Wiener. And then Donsker had this proof based on random walk. Basically we define B and T to be S N T by T, right? S N T by N. Sn is equal to summation xi. Xi is the IIT. Xi plus 1 minus 1 with probability. Then you can see, okay, B and T has variance which is T. The increments are more or less independent, modulo the boundary effects. And any distribution of the increment is Gaussian with variance which is given by the length of the interval. So it satisfies all the boundaries. So you expect this to work out. But with this B and T, okay, you can interpolate and get a continuous path. Now the question is, will the limit also be a continuous path? And this is kind of where the deconvergence theory kind of comes in. So limit in this abstract continuous C01 space, it's a Banach space.
No, except this directly follows from Kolmogorov's extension.
No, it requires a proof, no?
The Discrete is just it directly follows from Kolmogorov's extension.
I have to look at it. Some background must be there. It's not about to show them.
And it's specifically if you specify these finite dimensional marginals in such as stochastic process.
Let's look at the book together. Each B and T will induce a probability measure. We want to show that the probability measure is tight, and I've forgotten the details now, but it's never that straightforward. Okay, yeah, so Kolmogorov's, that extension theorem is used by, what you could do is, you can define a multivariate Gaussian process at each time period in a consistent manner. So then you get the finite dimensional distribution. And then you want to argue that there's again a limiting process. So maybe in that construction, the Kolmogorov extension theorem makes sense.
So the book says it directly follows from Kolmogorov.
So let's have a look. Yeah, but that's another kind of construction that you need to specify kind of multivariate Gaussian process in any finite dimension.
Okay, so this shows that such a stochastic process exists without a continuous requirement.
So without a continuous requirement.
And with continuity, they do some M6 type.
Okay. So yeah, so I'll look at it, right? If I say in the past, it's not there. Yeah. So anyway, so we're going to wash away all these things. But it's fun to read about these things, so you can do it on your own time. A great book to this is by these guys. Grazas and Sheep, right? So what's good about Gaza? You read it from here?
Yeah, but it's too hard to do.
Yeah. But what's good is that all the technicality are spelled out. He's not making any jumps. I mean, Oxendar jumps all the time. So it's not quite clear what is being said. But Gaza and Sheep is very precise. You just, now you probably read it, you'll follow it. You'll go a little slow. So Brownian motions to catch it. Okay, so this is, so we'll assume a construction. Okay. Some facts are kind of good to know that, there's this kind of self-similarity property. So if I look at BAT, and I divide by 1 by root A, yeah. Right. So I'm given a Brownian motion. I shift it by a positive number 8. And then I scale it by 1 by root 8. What I get is again a Brownian motion. This again is standard Brownian motion. Right? I mean, you can see 0 and 0. The increments are independent. Because they're independent here, they continue to be independent for this guy. Only thing you, and because this is continuous, this is continuous.
Why you are doing this thing? By
Well, to make sure that standard Brownian motion. So the scaling makes sure that you have this property. But you want to share that, okay, xt2 minus xt1 is distributed as normal 0, t2 minus t. Right? So to be able to do that, you need the scaling. You may check that, right? This is going to be a b a t2 minus b a t1. Okay. Now you know that this is Gaussian distributed, right? With variance which is given by a times t2 minus t1. Now you with this you divide by a, so get rid of a. So you get the t2 minus t1. Okay. More interesting thing, I'll just talk briefly about this, and let's go. Yeah, let's go. B of 1 by t, I think it's t. Yeah, t time. So this process also turns out to be standard Brownian motion. When you require now that x0 is equal to 0, because this is not defined for x0. 1 by t is not defined at 0. So you keep x0 equal to 0, then you'll find that this process also Brownian motion. What's interesting is that it's telling you that, okay, you know.
Yeah, how do you know the limit t goes to 0?
You have to prove that. You have to prove that. Yeah. I'll give you an intuition for it right now. Why that's true, but that needs a proof. I mean, if you look at this between 0 and epsilon, right? That's basically telling you everything that happens after 1 by epsilon time. So the initial process from 0 to epsilon captures what happens after for an infinite amount of time. So it's very fascinating, right? Brownian motion just captures everything in a small piece of information, as all the information already built. So we actually defined a process which has this property, we specified it, and it has this property. So it's very cool stuff in that sense. I mean, I've seen people kind of look at Brownian motion near 0 and prove large deviations for it, and use that to prove large deviations of Brownian motion, get a function of Brownian motion later on, or in the other direction. So this equivalence gets exploited in a interesting manner. But let's see. So about this, so continuity follows except at t equal to 0. The fact.
Actually, from law of identity, logarithms.
So let's see. I mean, so let's just take t, for example, to be 1 by n.
So,
We want to show x of 1 by n is converging to 0, right?
Yeah.
Now this, if this becomes 1 by n into b of n,
and b of n is like square root 2n log.
you can do it that way, or just think of b of n as kind of summation of x I equal to 1 to n.
Yeah.
And b1 is Gaussian, b2 minus b1 is Gaussian, b3 minus b2 is Gaussian, and they're independent. So now these are mean 0 variables. So by law of large numbers, it's going to 0. So that's the intuition. Now you need some more work to kind of, this is just one sequence. You want to show that no matter which sequence you take, this is going to 0. So you have more work to do. But at least it's now clear what's going on. So what's interesting, I guess, is I mean, it's clear if you spell out things, the increments are going to be independent. Because they're independent for this guy, so they'll be independent for xt as well. So what you really need to show again is that xt2 minus xt1 has the correct distribution. So that's going to be t2 b of 1 by t2 minus c1 into b of 1 by t, right? So how do you do this? We can think of this maybe t1 into b1 by t2. So t2 is bigger than t1, right? That means 1 by T1 is bigger than 1 by T2. So T1 plus, I guess, and I have T2 minus T1 into minus T1. Okay, now this is going to be independent of this increment. So mean zero is clear. This is mean zero, that's mean zero, mean is zero. So variance is going to go to check for. Now there are two independent variables. So the variance will just be sum of the variances. So variance of this guy is T2 minus T1 square upon T2. Variance of that guy is T1 square, I guess. And then upon T1 minus T2. And we know that this one should be equal to T2 minus T1, right? That's what we are hoping for. So we have 1 minus T1 by T2. Plus we have T1 square. So everything equal. T2 minus T1 comes common, this becomes 1 upon T1 upon T2. That cancels with this square. So you get it. Okay, so these are some transformations. Okay, so my agenda for today is basically, so I'll define martingales in continuous time, and that's going to be as you expect it to be. But then we want to show the kind of result that we show in discrete time in continuous time. And there's a lot of effort required to make that happen. So I'll show you how much pain that goes into it. Simply by talking about the stop martingale process. Remember, in discrete time, when we stop the martingale and stopping time, the minimum, so martingale at minimum of time t and the stopping time is also a martingale process. Now, just showing that in continuous time will see require a lot of work. And so I do work for that particular problem. I won't do work for other problems like the Dupes maximal inequality, Dupes LP, I just state them there, martingale convergence theorem. All of those can be shown. I'll just show them to you. I just state them here. Again, in steel it has those proofs. But the point is, once you have that, once you make those proofs, then you have the machinery available to you. Once you know that those things are true, then things become much more easy. You can do a lot of that. But to show them, you have to go through, you have to discretize everything and make it, the analysis work. So it's good to see how that's done. That's our agenda for today. I think we will end. So we need to have filtration. So this is clear, right? It's an increasing sequence of sigma algebras. Each ft belongs to a big F, right? We always have this omega fp space, right? And each ft belongs to big F, and then fs is less than ft if s is less than t. So ft is going, it's capturing information. So all that's filtration. And then we say that, okay, zero is adaptive FT is measurable with respect to FT quality. Okay. So now it's clear what we need to define a martingale, right? Need, so MD should be adapted, I'm assuming that. Then I need this to be true for all things. And second, I need these are basic properties that I need. And I'll say that my martingale MT is continuous if there's a set of omegas of probability 1. On those omegas, MT omegas is a continuous function of T. Okay, that's what MT continuous means. Okay, so something for Brownian motion. So again, I'll mention a few things here. I won't spend too much time on them, but good for you to see them. So reasonable filtration, reasonable FT is as follows. Smallest sigma algebra, which makes P of T adapted, right? So that would be this F of T here. Problem with this sigma algebra is, I can come up with another process AT so that BT is equal to AT. Probability is equal to 1 for all T. But this process AT need not be adapted, even though BT is. So those issues come up. So to get rid of that, what we do is we augment our sigma algebra with null sets. This is the main thing, but there are some similar other issues which also come up. So life becomes much more simpler if we just add some more sets to the sigma algebra. So what we do is as follows. Let me see how this. Yeah, okay. Let me look at this sigma algebra. On this sigma algebra, let me collect all the sets which have measure 0. Okay, so let's say A is all the sets A so that P of A. Okay. Now what I'll do is I'll collect all the subsets of subsets. Now those need not be my sigma algebra. Okay. So all sets B subset of A for some A.
Isn't it subset of a set in A also?
No.
With subset also has probability 0.
Then of course,
No, it's not measurable.
it's really measurable, right? That's what we are assigning probability 0 in a bigger, and we can set a bigger sigma algebra. So now it becomes measurable. So a lot of headache goes away once you do this. I mean, these measurability issues are very kind of real in continuous time, so one has to worry a great deal about ensuring that whatever sets you're looking at are measurable because of the issue of continuum uncountable sets. Okay, so we collect n is all sets of B and then assign P of B equal to 0 for B in n. And look at the sigma algebra, which is essentially so you have notation by three. Yeah. This n union with sigma B of S. P. So call this your f of t. For all. So this is augmented filtration. It has all the null sets, J and F0 itself. Okay. So now you don't have to worry about things. So now if indeed some process AT is equal to BT and BT is adapted, then AT will also be adapted. You can show that. In addition, with this you'll get this property that this f of t is equal to f of s greater. So this turns out, these two will turn out to be equal now. They were not true earlier. What's interesting about this f of t is that there are no surprises. You know, if there was jump at time t, all these guys would have seen it. And the intersection would have seen it. But f of t earlier would need not have seen it. But this guy, you know, this is right continuous in this sense. There's no surprises. You know, I have all the information that happened in time t that's captured in f of t. So that's those are the kind of nice properties that you get now. So you get right continuity when you kind of include all the concepts. So if your filtration has right continuity, if f of t is this, and it contains all null sets, then we say it satisfies the usual conditions. So if you talk to people in this community, they say my filtration satisfies usual conditions.
So user condition. All null sets are included.
All null sets are included and you have right continuity. So yeah, I guess people didn't want to repeat all this and they just said, let's call it usual condition. Yeah. But I mean, you kind of said yourself, okay, you know, we've got ourselves unnecessarily to these measurability issues, which we don't want to be in. So how do we at least have some simple fixes? So this is a major fix. Now that we have this out of the way, now let's talk about stopping times. So stopping times now are no longer integer value, right? These are random variables. So omega is being mapped to now the non-negative real line. And it could also you have to take by infinity as well. Stopping time. If t so this is as we defined it in this P test. So if ft is all the information that is available to us at time t, we should know whether we stopped or not unambiguously. That's the stopping time. This is not, now we are saying tau omega equal to p is in ft. That's not the same thing anymore. In finite, in discrete setting it was. So you could have also defined another kind of variable. So I can have a random variable tau with this property as opposed to this property. These are called optional types, optional sampling types. But when you have right continuity, then you can show that both are going to be the same.
If the productive process is continuous, then the association is always electron.
What's that?
If your stochastic process is continuous with probability 1,
Yeah,
then so is understood that the filtration is
that's right. If the
I can
filtration,
ask it, sir.
if the filtration corresponds to the stochastic process, just if it corresponds just to the stochastic process, then that should be true. If your filtration is bigger than that, then it may not be true. It may contain other information also.
Yeah, the one generated by the sigma.
Yeah. Yeah, no. Yeah, I think that can be proved because there are no surprises, right? You see, it's continuous, so you see everything. Yeah. Right. For most practical purposes, everything we do in computer science systems and is practical. I think right continuous function with left limits is enough. So those jumps are enough for us. So we are saying continuous, but we could generalize things to right continuous function with paths so that they have left limits and they're right continuity. So some technicalities do come up. We're just not focusing on them right now. I mean that's a full course is not in motion. But a good book, as I mentioned, is Kratz's and Sri. Okay. And it's clear now how we define this process, right? X, omega. Then okay. Okay, so now the result that we want to prove. Was right? Seems like a not worst thing to prove, right? But kind of shows you how does it show something like this in continuous setting. So what do we need to show? We need to show one of xt is less than infinity for all t. And 2 we need to show. And I guess we need to show xt is adapted also.
Yeah.
Huh? That's okay. We'll ignore that.
The second one is less than equal to 50.
Was that?
The
Yeah.
second one, yeah.
So we just have to show these two things. But they're very nice ideas that are given in scheme here and there, which help us do this. So they're good to see. That's kind of the way I am going to do this in some detail. So first thing is, of course, clear. What we do is we extract a discrete time process. Right? So we construct Sn to be all times of the form S plus T minus S K upon bar N, or K between minus infinity to infinity integer. So S and T are in this grid, and this grid has step size of 1 upon 2 to the power n. So if we just look at this process on this grid, the empty process, it's a martingale step. You can still have martingales. That's what we will exploit. Okay, and then we'll observe that we'll define tau and omega to be minimum A in Sn is that is equal to tau omega. So it's a point on the grid which is just ahead of tau omega. So you stop just before this. You look bored. You've seen this before all of this stuff. So is it clear that tau is a stopping time?
Yes.
This is going to be less than equal to t. So think about this way. This is your picture. Yeah. Let's say t tilde plus 1 by 2n, so on and so forth. And suppose this is your tau omega. So if tau omega is this, then tau omega is this guy here. Right? So this guy is less than or equal to t. If this guy is less than or equal to t, if and only if t is somewhere here, t is somewhere in all of these places. What do I want to say? I want to say that
You just look at the read point right before tau omega.
tau omega less than or equal to t is equal to tau omega less than or equal to, I guess, t and t, where this is the point on my grid just before t. So if tau is less than this point, then tau omega is less than or equal to t. And if tau omega is less than or equal to t, then tau omega is less than or equal to this point. So is this clear? So what am I saying here? I'm saying that t is here. This is my grid points. And T and T is. Did I say just before or did I say just after? I said. I think I said this point here. So this is my T, and this is a point which is just before T. Okay. So if tau omega is less than or equal to this point here, then tau and omega will be less than or equal to T. Because tau and omega will just look at all these points and jump to the next grid point, right? If my tau omega was here, then my tau and omega will come here. So if my tau, yeah. So if I tell you that my tau and omega is less than or equal to T, that must be because tau omega is less than or equal to T and T, this point here. Okay. So this is an FT. Because T and T is less than T. So hence this is measurable. Hence this is a stopping time. I mean, the point again is if my tau omega is here, then my tau and omega is just here. That's the point. It's cross T. So if I tell you that my tau and omega is not cross T, that must be that my tau omega is before this. Yeah, that's all. Okay, so that's the good thing that tau n is a stopping time and tau and omega is decreasing to tau omega. It's getting closer and closer to it as n goes to infinity. So those are properties which are going to help me. And one thing you can do if you're interested in this kind of stuff is just maybe to take a reading course. I'm not on, but maybe with someone or on your own, where you read classes and She and those kinds of books and go through this stuff in slow and very detail. I mean, it's good to know this stuff if you're interested in continuous time, so basically equation and stuff. Okay, now we've got these properties, right? So now what am I going to say? What am I going to say now? Okay, so I'm going to look at MU, SU in the martingale or U ligand SN. Okay. So in particular, I get that okay, E of n T min tau n this is just discrete time theory. It's just a discrete time Markov chain, discrete time martingale. So I get this property. So from this I can conclude the
Or is it exactly?
absolute value. Sub-martingale. So this, how does this follow from here?
E of model T is less than infinity.
Yeah, that of course is given to us, right? Yeah. But how do I get rid of n?
Limit n goes to infinity.
What's that?
Monotone convergence.
What's monotone here? What's dominant here?
For that, you need it to be counted everywhere.
Yeah, for each omega.
Yeah.
What do I know?
Yeah, you have a decreasing.
I have a So I know tau n is converging to tau. And I know I have a continuous time martingale. Continuous martingale. So that means this is converging to m t omega by omega.
But you need convergence to mean.
So this is almost surely as n goes to infinity. So now how does this follow?
Uniform integral.
Uniform integral. We've not shown that yet. Is there something easier that kind of helps you do this? This bound is true for every n.
Very long.
I'm looking for a word.
Okay. So it can be said that for n larger than this is less than like 1000.
So this guy is nothing. You agree that this is nothing but this guy, right?
Oh, fuck.
Yeah. But two has its uses, yeah. Right. This is going to be dominated by this guy outside, limit outside, and that's going to be dominated by this guy. This bound is true for all. So at least
And
this,
non-negative.
everything else absolute value, right? It is non-negative.
Oh.
It's all absolute value. Okay. This we get from. So we get one condition. Now we need to show this. E of m p min tau n given fs is equal to, well, this we have, of course, m of s min tau. This we have from discrete time analysis. We want to show that this is true. Okay, this is what we want to show. Almost surely. Yeah, that's true. So if you take limit of this guy, you get this by continuity.
And conditional variables are also convergent.
And also
Convergent.
that we don't know yet. So right now we don't know if this is converging to this. We need to show that. If we had that, that will be done. So we want to show that this is converging to this. And suppose I could show this is converging to this in L1 or L2, but let's call it L1 because we don't want to assume L2 or anything. We don't want to assume second moments right now. We want to put things much more generally. It's much easier to put things if you assume that everything is L2. But suppose I could show that this is converging to this in L1. Why is that enough? Then, because I want to show this is equal to this almost surely, right? This is converging this almost surely. It's everywhere actually. So if I can show that this is converging this in L1, then there's a sequence, then it's converging this also in probability. And then there's a subsequence along with this is converging this in almost surely by Burke and Terry.
Continuity.
No, so along that subsequence, this is converging this almost surely, that's converging this almost surely. So these two must be true. So convergence in L1 is enough. I think I just want to make that case. So and to show convergence in L1, so I need to show you. I want to show that this is going to 0, right? This then goes to infinity. And you can see that this will follow if I just show right? Because by Jensen's you can upper bound it by this. So this is going to 0, this is going to 0. And this means that so one way to show this is just to show that
condition.
what's that?
How does the condition?
By Jensen's, right? I just bring this absolute value inside and then I'll take the expectation. Yeah. So that's how. And for this, it's sufficing if I show you that this sequence of random variables is uniformly integrable.
Convergence probability plus uniform.
Yeah, I mean, I have convergence almost surely here. This is
probability.
would be enough, yeah. But since this is convergent, this, if this was uniformly integrable, I'd be done. So now how do I show uniform integrability of this sequence? That's what we are right now. And this is where again there's a nice idea. So there are a sequence of things. So one is, of course, if I can show you, so I'll generalize things a little bit from what we've done already.
You're recording the later, right?
Yeah,
I will see the recording.
sure. Okay. So suppose, so let's come up with the function phi of x, so that phi x upon x is going to be plus something. And phi of x can be non-negative, it can actually be strictly inclusive. I think that will be fine. You don't need it to be, but if we have that, that's perfectly fine. And now if I can show you that for let's collect, so let's see is a collection of random variables. If I could show you, if I have that supremum x in C, phi of x is less than infinity. I just call this equal to p is less than infinity. Then my collection of random variables is uniformly integrable. So I'm giving one more condition for uniform integrability. Up till now, we just had that, okay, if 1 plus epsilon bound was each random variable, if the 1 plus epsilon moment was uniformly bounded, then I get uniform integrability. So that would be a special case where phi of x is equal to absolute value of x raised to power 1 plus epsilon.
The previous condition is the supremum phi of mod x indicator function, mod x greater than p.
That's the definition. But one sufficient condition we did was this. Yeah, so that's the definition of uniform integrability. So we're saying that this will also suffice to show uniform integrability. Let me just make sure I'm putting the mods in the right place. Yeah, this sounds correct. All right. So recall, where are we going with all this? We have this stopped process, empty minimum tau n, and we want to show that that collection of random variable is uniformly integrable. Then we have proved that's a martingale. That's very good too. That's where we are right now. Okay. So let's look at P of absolute value of x indicator x is greater than equal to k. Right? Or let's put x is in C. Okay. I want to show that this implies uniform integrability. This is this because I have now. So let me call my psi of x to be equal to phi of x upon x. It's a new function. So I can rewrite this as equal to expected value of phi of x upon psi of x. Nothing has changed. This is just equal to this. Second bound by this B here, to minimum of x. Okay. We'll just use small x here. Okay. Right. And now, because this is going to infinity, as x goes to infinity, this term is going to infinity as k goes to infinity. Okay. So I get my uniformity given. So it's good to see. It's it's a very simple thing, but we've extended that whole idea somewhat, the earlier sufficient condition, just by this. You could just take the minimum out here that you're done. So that's good to know. The other idea which was interesting was this, that if I tell you that for random variable e of x is less than infinity, then this is a very nice idea. Then there exists a function non-negative convex function phi such that such that phi x upon x goes to plus infinity, and e of phi of x or phi of x. Just stare at this for a moment. See, all you're given is e of absolute value of x is greater than 0. Is finite. And I'm saying there's a nice function phi such that phi of x upon x is going to plus infinity. So it's super linear. And it's convex. And e of phi of absolute value of x is also less than infinity. Now you can ask yourself, can I recurse this? It can recurse this, right? Now this becomes my new x. And I get one more phi on top of that. I get one. So potentially there's a good theory to understand all these things. And you can keep on doing this, but in the limit, of course, you get something which doesn't work. But in any case, such a phi can be found out, and we'll find that phi right now. It's kind of nice, right? It's that you can always squeeze such a function out, and it's convex. For every random variable, we can do that. For every one random variable, we can do that. So we'll go back to our stopped process. We'll bound it by a random variable. For that random variable, we'll find a phi. And then we'll use that phi for our stopped process. That's one thing. Okay, so how do you find this phi of x? It's not so straightforward, right? Right. E of z is just 0 to infinity.
E of x is expectation of x to a condition not executed.
What's that?
The phi of x is the expectation of set condition on z mod z and equals to x.
That will work. I mean, that will have to be finite, that's true. Right. mean, that's a slightly different statement from what you have said. You're not coming up with a phi for me. You just think that okay, if unconditional expectation is finite, then conditional expectation also will be finite. So this is given to me. What I'll do is I'll construct a function p of x here. Where p of x increases to infinity as x. And this is finite. So first I'll do this. And then I use this to construct my phi. Essentially phi of x is going to be equal to x in since this is going to infinity as u goes to infinity, phi of x upon x will go to infinity as x goes to infinity. If I just divide it by x, that if a of u is going to infinity with u, then this divided by x will also go to infinity with x. Right? Because what do I want to show? I want to show that this is bigger than any bound n. Okay. Right.
So you take in prime and say u is greater than equals to u in prime for our u
Yes.
greater than in the right hand side you can go from left hand side.
Whatever remains on the left hand side is going to die out in any case.
Right hand side you can go.
Yeah. And what's so you can take 0 to m prime and then m prime to x, and all your contributions coming from m prime to x, and then your a of x is big enough. So when you divide by x, you get that bound. You choose your m prime in that manner. So this is going to work, and then we'll see that this condition will basically mean that u of n is equal to this, and hence it is this. So really, the crux is going to be right. I'll just complete this part here. So you can see that this is same as saying that okay, 0 to infinity, 0 to absolute value of z, e of x, dx. Because 0 to z, this thing is just the indicator function that z is greater than or equal to x. So I can so this probability I've written as indicator function, and the expectation I've taken outside. Everything is non-negative, so by Fubini I can do that. And this is just same as saying that my x can go only up to the absolute value of c. So this becomes dx, and this is nothing but phi of absolute value of c. But there's no integral.
Where did the first integral?
This integral became 0 to absolute value of c. The expectation came outside. So this is exactly equal to e of c. So all I need to do is basically come up with that a of x. So my phi of x is now, phi of x is defined as follows. So phi prime of x is equal to a of x I'm choosing my a of x to be strictly increasing with x. So that tells you that it's a convex function. My phi is a convex function. It's increasing is all I need. It's increasing with x, so it's a convex function. Okay. So what do I need to do? Basically, I need to construct such an a of x, basically. Okay, I'm given this, and I need to construct this. And then I'm done. These are all kind of nice ideas which one wonders can one come on with on one's own. They look that obvious. All of them have this extra twist to them. So what's a of x going to be? So it turns out this is going to work. 1 upon. This one. Yeah. So now you can see that your a of x is increasing with x, right? I mean, this could just become 0, in which case your a of x is infinity and stays infinity. It's not decreasing at least, still not decreasing. Now, look at my integral 0 to infinity a of x. I want to show that this is finite. So one more clever idea. Let me define x of k equal to infimum x. As I increase my x, this will become smaller and smaller. So first time it becomes less than 2 to the power minus k, I call it xk. I get this whole sequence of xk's. So now let's come back to this. I can rewrite this as summation k equal to 0 to infinity integral xk plus 1 x you see it now? Pretty nice, huh? A of x nothing but integral x to infinity, right? Yeah. Now within this limit, I can, I want to upper bound this, so I'll put, I guess, xk plus 1 here, right?
Yeah.
Okay. And then this thing is going to be, okay. How am I doing this?
1 minus x.
Right, so that's, because this x is less than xk plus 1, this thing is right now bigger than 2 to the power minus k plus 1. So then I can write this as 2 to the power minus k plus 1 to the power alpha, move this, and this guy here is bounded by xk2, this is 2 to the power minus k, 2 to the power k, 2 to the power minus k, 2 to the power, yeah, this becomes plus and this becomes minus k. Right? That's just 2 bar alpha equal to infinity minus alpha. K alpha, it's increasing, minus k dominates this guy. 2 to the power alpha is just a constant that just comes outside. So we've shown that this whole thing is going to be finite. Integral ax dx. So you've got this quantity here, because x is bigger than xk plus 1, right? So this quantity here is bigger than 2 to the power minus k plus 1 to the power alpha. So I just plug 2 to the power minus k plus 1 alpha, I get an upper bound. And then this quantity here from xk onwards is dominated by 2 to the power minus k. Yeah. Yeah. It's the kind of stuff you hope you can use somewhere now that you've seen it. It's nice.
Just for showing uniform intelligibility.
Yeah, so we're now showing uniformity now that we've done all this. Okay. The point is, right. So we wanted to show this, that this sequence, if you want, we know that, okay, we have this, we have this, that. So some martingale, so we have this properties. But this was not enough to show that this is UI. But for this guy, we can construct a phi. So the E of phi of M of t is finite. And it's because phi is convex, this process is also a super martingale. I mean, I guess E of M of S, let me call it. S lying in Sn. This process is some martingale.
Are you saying M mod T and pi is a submartingale?
Yeah.
But saying just restricted to T that lies in the
Sn, yeah. Yeah. F absolute value MS is a submartingale. All S is in Sn. Because phi is a convex function, you can just use Jensen's and check this. So what you get now is that this thing for M of t we constructed this phi, right?
This is also only for T in the lattice.
Yeah. S and T we fixed. We're just showing things for S and T right now. S and T is fixed, we constructed a lattice. That's all. Yeah. They both belong to the lattice. So we constructed this phi. This we know is true. So this is your B now. Now for each n, this is true. Right, I could have constructed this whole concept, this stuff, and taken the same thing. So I get that this sequence mt min tau n is uniformly integrative. Okay. And hence mt min tau n is converging to in L1 mt min tau.
So we have to show that the conditional into variables in T and tau and conditional is.
No, that we already argued that they will. It suffices to show that mt min tau n is uniformly integrative. Lots of layers and more than this. So we are done. Basically, we just needed this guy to be a sub-martingale. Right, so what does that mean? We need P of M of, I guess let's call it T. Given that T minus 1, I'm just calling it T minus 1 right now. Let's give them equal to phi of M of T minus 1. That's what we need for some martingale. T minus 1, I mean on the lattice. But this will follow because I can, because phi is convex. This is basically getting phi of E of absolute value of M of T given mt minus ft minus 1. And that's given equal to absolute value of mt minus 1. So I get this. So yeah, it's as with everything, it's a tower of Babel, it's constructed 1 year old. This is second discussed chapter on Brownian motion, I guess. There are two, there's first chapter on Brownian motion, and then there's a second chapter on Brownian motion. So steel. So everything is from steel, I guess. Steel is a much nicer book to read than classes and sheet. And also much nicer than the other book that you mentioned. What was it? Oxendal. Oxendal is annoying. Okay, so we are done on this. Now we can do other things too, which I will not show, but you can see in steel. Things like, okay, probability that soup S between T and 0 M of T is equal to lambda is equal to E of E. This is the maximum inequality. And then this is a continuum, that's the way. Martingale's chain LP. This is groups LP equal. And then you also have a similar convergence. I won't write it down right now.
This also is for other things.
This is for some martingales. And I guess similar result will hold for super martingales. The village theorem will hold for super martingales. I've not done the math, neither has the book, but I would imagine it would be true. Right. Okay, so this is it for now. We'll meet next time. We'll do some Brownian martingales, I'll talk about one cool principle in Brownian motion is the reflection principle. You know, I may have mentioned this earlier, right? So you have a Brownian path like this. I can, just have a plane here and cut this path and reflect it on this. The probability of this path is same as probability of that path. It's along this thing, right? So this is going up, this is going down. This is the reflection across this axis.
Oh,
Yeah. So we'll see how this helps us, for example, talk about, this quantity then becomes very easy to deal with. And joint distribution of the maximum and a marginal. So those kinds of quantities are generally of interest. In Brownian motion, they have a nice closed form. That's the power of Brownian motion. You get elegant results. So we'll do all of that the next time. What I wanted to do, but I won't have time to, is just prove the fact that Brownian motion is everywhere continuous on a set of probability 1, but nowhere differentiable.
so you don't even define.
Huh?
You don't construct.
Yeah, I'm not even constructed Brownian. So, but if you assume the construction, then you can prove that with this construction, the process on a set of probability 1 is not differentiable at any time t. So that's a nice result, right? It's not kind of, it's very noisy.
It will oscillate around the frequency.
Yeah. So they're very interesting properties. I just mentioned them. You can read them on these books on your own. Okay. So that's the plan. You get an exposure to Brownian motion. Okay, guys. Any questions from your side? Are you Shantanu and Sunanda? Are you not in Mumbai or?
I am here actually. I'm feeling unwell.
You're sitting in your room.
Yeah.
Okay. And Shantanu, where are you?
Yeah, I'm actually doing some. Actually, I have some health issues, so I could not able to come to the class.
Sorry, I couldn't make out what
Hello.
you said, Shantanu. Yeah. I can hear you, but your
Oh,
voice is
actually,
not.
sir, I have. Hello.
Yeah,
Hello,
go ahead.
sir?
I can hear you. Go ahead, just say what you're saying again.
Oh, actually, sir, I have some health issues, so I could not able to come to the class today.
Okay, you could not come to class, but you're on campus.
Yeah, I'm on campus here.
Oh, good. Okay, well, chalo, we'll meet on Friday for the last class at 2:30 p.m.
Is my presentation on May 16th or May 11th?
May 11th, right?
Yeah.
Is that okay?
No,
or you?
Yeah, that's fine, sir. The point is, you said that it's on Monday, so.
No. Because you want your May 11th, so yours is on May 11th on Wednesday.
Yeah.
At 4 p.m.
Yeah, okay, fine.
And then there's another presentation by Augmented on May 16th at 4 p.m.
Okay. Okay, sir, fine.
Okay, guys. Chalo, so we'll be in touch day after tomorrow. Bye.